So when it comes to training these giant AI models, you always hear the same thing, right? Bigger is better, faster is better. But what if I told you that the race for pure speed might actually have a hidden cost? We're about to dig into a really fascinating discovery that shows there's this crucial trade-off between making an AI fast and making it smart. Let's get right into it.
And really, this question gets right to the heart of the issue. I mean, think about it. We're relying on algorithms for more and more stuff. So of course, we need them to be powerful. But we also have to be able to trust them. And you can't really trust something you don't understand. So the big question is, can we actually have it both ways?
All right, so here's our plan. First, we're going to talk about a type of AI you can actually wrap your head around. Then, we'll look at the huge data challenges that we're all facing today. From there, we'll walk through this massive experiment designed to tackle that, uncover a really surprising trade-off, and finally, connect all the dots to see what it means for AI in the real world. Okay, let's kick things off with a model that isn't some mysterious black box. It's called a random forest. And one of its best features is that you can actually see how it thinks. And look, this kind of transparency isn't just a nice-to-have in some fields. It's absolutely essential. Imagine you're a doctor, and an AI suggests a pretty serious treatment plan. If that AI can't explain why it came to that conclusion, how can you possibly trust its recommendation? You can't. And that's exactly why researchers often lean on these more understandable models. So the basic building block of a random forest is something called a decision tree. And honestly, it's pretty much what it sounds like. It's like a flowchart for making a decision. It just asks a bunch of simple yes or no questions, one after the other, until it lands on an answer. Super simple and really easy to follow the logic. Okay, so if one tree is like a flowchart, a random forest is basically a whole committee of them. We're talking hundreds, sometimes even thousands, of these individual decision trees all working together. Each one gets a slightly different perspective on the problem, and then they all vote on the final prediction. It's this teamwork that makes the final result way more robust and accurate than what any single tree could manage on its own.
So these understandable models sound great, right? But they're running up against a massive problem in today's world. Our data has gotten way too big and way too private.
You know, there's a basic rule in AI. The more data you can feed it, the smarter it generally gets. But we're now creating data sets that are just monstrous. We're talking millions of data points, and they're so huge they can't even fit on a single computer anymore. We've basically hit a wall.
And it's not just about the sheer size of the data, right? It's also about privacy. So much of our most valuable information, in healthcare, in finance, it's incredibly sensitive. You can't just pool it all together on one server. And as the research here points out, this challenge has given rise to this really powerful new idea called federated learning.
Let's make this really concrete. Just imagine Hospital A. They've got tons of valuable patient data, which would be amazing for training a diagnostic AI. But for very good reasons, privacy, security, that data is not allowed to leave the hospital's own computers.
Now, let's add Hospital B and Hospital C to the mix. They've got their own data too. If all three could somehow combine what they know, they could build an incredible AI. But again, they can't share the raw data. So how do you get them to work together? That's the million-dollar question, and it's the exact problem federated learning was created to solve.
So that's the setup. This brings us right to the experiment at the center of all this, where researchers decided to see if they could train one of these massive random forests by spreading the work across a whole network of different computers.
And this wasn't some small-time test either. I mean, they really put this thing through its paces. They scaled it up to 64 different computers, or nodes, all working at once. They threw these enormous data sets at it, some with up to 7.5 million data points. But here's the kicker. They really wanted to see if how they split up the work would change how smart the final model turned out to be.
So the main idea they tested is actually pretty clever and elegant. It's called a tree parallel approach. The logic goes like this. If your random forest is made of, say, 1,000 trees, why make one computer do all the work? Why not have one computer train the first 100 trees, another computer train the next 100, and just keep going like that? You split up the model itself, not the data.
And wow, the results for speed, well, they were seriously impressive. By spreading the training out over 64 machines, they got things done nearly 32 times faster than a single machine could. So yeah, it proves that this method is incredibly good at speeding things up.
But here's what's maybe even more impressive, the efficiency. They measured something called weak scaling efficiency. It's a bit of a technical term, but basically it asks, as we make the problem bigger and give you more computers, can you keep up without slowing down? And at over 96%, the answer was a resounding yes. The system was a champ. It just kept going.
Okay, so everything's looking amazing, right? It's faster, it's super efficient. But then, right in the middle of all this success, they stumbled onto something totally unexpected. A hidden trade-off between how fast you train the model and how smart it actually becomes.
And it forced them to ask this really critical question. We know we can make things go faster by splitting up the model. But what if we also split up the data to try and get even more speed? Does the strategy we use to divide and conquer the problem actually change the quality of the final answer? And this slide right here lays out the answer perfectly. On the one hand, when they only split up the forest, so every machine could still see all the data, the model kept getting better as the data set grew. It was a bit slower, sure, but it was learning. Now look at the other side. When they tried to get even faster by splitting up the data too, giving each machine just one tiny piece of the puzzle, well, the AI stopped getting smarter. It completely wiped out the benefit of having more data in the first place.
So the big takeaway, the thing you absolutely have to remember, is this. The fastest way to train an AI is not always the smartest way. If you give each part of your model only a tiny, isolated glimpse of the data, it never gets a chance to learn the big, complex patterns. It just can't see the full picture.
Okay, so this is all super interesting. But what does it actually mean for us in the real world? Because let's be honest, real-world data is never clean and perfect. It's messy. And this discovery has huge implications for dealing with that mess.
Yeah, there's a technical term for this messiness. It's called Non-IID data. It sounds complicated, but all it really means is that data from different places usually looks pretty different. In the real world, things are almost never perfectly balanced.
Let's go back to our hospitals for a second. Think about it. Hospital A might be in a retirement community and sees mostly older patients. Hospital B might be downtown and sees a much younger crowd. As you can see from these charts, their data is going to look completely different. And that imbalance makes it so much harder to train a single good model, and it makes your choice of how to distribute the work even more critical.
And that leaves us with this huge, fundamental question for the future of AI. As we build these incredible collaborative systems that protect our privacy, we're faced with a big choice. Do we prioritize raw, blistering speed, even if it means our AI might not be as smart as it could be? Or do we choose the more thoughtful approach, making sure our models get the whole picture, even if it takes a little more time? The answer we choose is going to define the future of AI.